Hello everyone, I welcome you all to this video lecture. In this video lecture, we are going to study an important finite word length effect, that is limit cycle oscillation behavior in recursive systems. So first let us understand what is meant by limit cycle. Okay, so during the periodic oscillations, so oscillation means it gets oscillated between two levels or it remains a constant value as the n value gets increased. Okay, so such oscillations are called as limit cycles. Okay, so these oscillations will occur due to two processes, that is due to round off errors in multiplication process and due to overflow error in addition process. So if we study limit cycle in multiplication process means that will occur due to the round of errors. In case of addition means it will occur only due to the overflow error. Okay. So these limit cycle oscillations can appear only if the filter has feedback. So already we have learned two types of filters. One is recursive filter and non-recursive filter. There is FAR and IAR filters. So always remember FAR filter cannot have limit cycle oscillation because it does not have a feedback. So this limit cycle oscillations will occur only in IAR filters. So there are two types of limit cycle oscillations. That is zero input limit cycle and another one is overflow limit cycle. So now in this video lecture, we are going to study zero input limit cycles. So from the name itself, you can understand zero input. Okay. So for example, consider a recursive system. Okay. We are giving some input. Definitely you'll get some output from the system. Now we are removing that input or we are giving zero input to the system. So what happens? Actually, there should be zero at the output, but this is not the case. Here there will be some oscillations at the output. So these types of oscillations are called as zero input limit cycles. That is, we are giving only zero input, but at the output there are some oscillations. So that we are calling it as zero input limit cycles. So the second one is overflow limit cycles. So already I have said the limit cycle is occurred due to the round off error in multiplication and overflow error in addition. So this is the second case, that is overflow limit cycle oscillation behavior. So in fixed point addition of two binary numbers, normally overflow will occur when the sum exceeds the finite word length of the register. So this overflow in addition lead to the oscillation at the output. So this oscillation is called as overflow limit cycle oscillation. So next we are going to see an important definition, deadband. Already we know limit cycle will occur between a positive value and a negative value. That is, it oscillates between positive value and negative value, or it remains a constant value. So we need to find out the range. So for that purpose, this deadband is used. So deadband is equal to plus or minus 2 power minus b divided by 1 minus modulus of a. So that is minus 2 power minus b divided by 1 minus modulus of a to plus 2 power minus b 1 minus modulus of a. So this is the case for first order system. So first order system means it has only one pole. So y of n is equal to a into y of n minus 1 plus x of n. Right. So for this is the deadband. So here b represents the number of binary bits. So here you have to remember one thing. Here the number of binary bits means it is including the sign bit. So normally for negative numbers, we will be representing sign bit as 1. Positive number means sign bit is 0. So including the sign bit, the total number of binary bits is represented as capital B. Okay. Now, if we consider for second order system, so we are having A1, A2. So the deadband is calculated as plus or minus 2 power minus b divided by 1 minus modulus of A2. Okay, right. Then we have to take the second pole. So A2. So that is equal to minus 2 power minus b divided by 1 minus modulus of A2 to plus 2 power minus b divided by 1 minus modulus of A2. So this is a very, very important 2-mark question. That is deadband of a filter. So now we are going to solve a problem. So understand the question clearly, then you can proceed it. It is very simple only. So first, explain the characteristics of limit cycle oscillation with respect to the system described by the equation y of n equal to 0.95 y of n minus 1 plus x of n when the product is quantized to 5 bits by rounding. So here the quantization is done up to 5 bits including sign bit, right? The system is excited by the input x of n equal to 0.75 when n is equal to 0, and for remaining n values, its value is equal to 0. Now, determine the dead band of the filter. Okay, so this is the question given. Okay, actually this question is a repeated question. So understand a single question thoroughly so you can able to answer any question, right? Okay, so given y of n is equal to 0.95 y of n minus 1 plus x of n, right? So here the recursive realization of the given system involves the product 0.95 into y of n minus 1. So here there is a multiplication. We are multiplying 0.95 with y of n minus 1. Okay. So now consider y of n be the response of the system when the product is quantized by rounding. So we are going to multiply these two terms, that is 0.95 and y of n minus 1. Then we are going to apply quantization, that is rounding. Okay. Then we are going to find out the value. Okay, so y of n is equal to quantized Q represents quantization. Q of 0.95 into y of n minus 1 plus x of n. So where Q of stands for quantization of product. Okay, now given the products are quantized up to how many bits? 5 bits it is given. So 5 bits means normally we will be using sign magnitude representation. So sign magnitude representation means first bit represents the sign of the number, that is either positive or negative. If it is positive means its value is equal to 0. If it is negative means its value is equal to 1. Okay. So now we are going to use 4 bits for magnitude and 1 bit for sign. So that totally we'll be getting 5 bits. Okay. Then given x of n is equal to 0.75 for n is equal to 0 and y of n is equal to 0 for n less than 0. That is for n is equal to minus 1, n is equal to minus 2, y of n value it will be equal to 0. So these are the conditions we are assuming. Okay, to draw this table. Okay, so in this table, first n value, then x of n, y of n minus 1, 0.95 into y of n minus 1. Then we are applying quantization. After quantization, we are finding what is y of n. Okay, so for n is equal to 0, first, initially, n is equal to 0, we know when n is equal to 0, x of 0 is equal to 0.75. It is given in the question. Okay. Then when n is equal to 0, y of minus 1. So for negative values of n, y of n value is assumed to be 0. So y of n minus 1. N minus 1 is nothing but previous output. Its value is considered as 0. Now 0.95 into y of n minus 1, 0. Then again we are quantizing it. So you'll get 0. Then what will be y of n? Y of n is equal to x of n 0.75 plus this quantized value. So you'll get 0.75. So first iteration over, that is for n is equal to 0, this is the answer. Next, for n is equal to 1, we are going to see. So this is the case for n is equal to 1. So when n is equal to 1, in the question it is given for n is equal to 0 alone, x of n is equal to 0.75. So for all other remaining values of n, x of n is equal to 0. So y of n minus 1. So y of n is the output means then what will be y of n minus 1? It is the previous stage output. So y of n minus 1 is 0.75. So we have written 0.75 here. Next, 0.75 into 0.95. We are multiplying it and we got the answer as 0.7125. Now, here you are going to apply quantization because quantization of 0.95 into y of n minus 1. So we are going to apply quantization and going to find out the answer here. So the procedure is 0.7125. first convert it into binary. Okay. So we are converting it into binary. Then we are adding this sign bit. So it is a positive number. So sign bit is equal to 0 only. Now, at how much bit we need? We need 4 magnitude bits and 1 sign bit. So totally 5 bits. So round off this to 4 magnitude bits. So round off process means just we are going to add the last bit to the previous bit. So you'll get 0.1011. Then again, we have to extract the sign bit. So sign bit is equal to 0 only because it is a positive value. So we are neglecting that. So 0.1011. Now convert this into decimal value. So if we convert this into decimal value, we'll get 0.6875. So this is the decimal to binary conversion. We know how to convert it, right? 0.7125 into 2. We have to multiply it. Then again, that value into 2. We have to multiply it. Then again, this point decimal value into 2. Then into 2. So finally, if we go like this, you'll get the value that is 10110. So that is our answer. That is binary conversion, decimal to binary conversion. Now, binary to decimal conversion. Again, we have to convert it into decimal value. So for that, we have to multiply by the weight. That is that position weight. Here 1 into 2 power minus 1, 0 into 2 power minus 2, plus 1 into 2 power minus 3, plus 1 into 2 power minus 4. Then we have to add these values. So finally, you'll get 0.6875. So in the previous iteration, we got the answer as 0.6875. Now we go for the next iteration because we didn't get the constant value at the output, right? That is the last column. We should get a constant value. Otherwise, we need an oscillating value. So here we didn't get any constant value. So we go for the next iteration. N is equal to 2. So again, when n is equal to 2, x of n value is equal to 0. So what is the previous output value? Previous output value is 0.6875. Then again, it is multiplied with 0.95 and you'll get 0.6531. So here again, you are going to convert this into binary and after that you have to apply quantization and again you have to convert it into decimal. That is like this. For n is equal to 2, 0.653125. Convert it into binary, you'll get a binary value, then sign bits. Here again, it is a positive value. Suppose it is a negative value, means you have to add 1 here. That is 1 point something. You'll get like this. Okay. Then round off it to the 4-bit value. So finally, convert it into decimal. So you'll get 0.625. So this is the decimal to binary conversion and this is binary to decimal conversion. So finally, you'll get the answer as 0.625. So here for the second iteration, we got the answer as 0.625. Now we go for the third iteration because we need constant values at the output. Then only we can stop our iteration. So now we go for the third iteration. So for third iteration, the previous value, previous output is taken as 0.625. Then it is multiplied by 0.95. So we get 0.59375. Then we have to apply quantization. We have to convert it into binary. Then we have to apply rounding process. Then finally, you have to convert it into decimal. So that process explained here. That is 0.59375. Convert it into binary. You'll get 0.10011. Then sign bit again. If it is a positive value, means sign bit is equal to 0. If it is a negative value, means sign bit is equal to 1. Now round it up to the magnitude up to 4 bits. So finally, you get the answer as 0.1010. So convert it into decimal value. After applying the quantization process only, we have to convert it into decimal value. So finally, the answer is 0.625. So here again, we got the same answer. So we can stop our iteration at n is equal to 3. Now, if you go for n is equal to 4 also, you'll get the same answer. So we can stop at this iteration. So next we are going to calculate the deadband. So from the above calculation, it is clear that for n is equal to 3, our output is constant. So the value is 0.625. So the system enters into limit cycle when n is equal to 2, right? So the deadband formula is plus or minus 2 power minus b divided by 1 minus modulus of a. So we know b is equal to 5 and modulus of a is 0.95. When we apply this value, we'll get the answer as plus or minus 0.625. So our deadband range is minus 0.625 to plus 0.625. So this is the zero input limit cycle oscillation behavior. I hope you all what is limit cycle oscillation and what are the types of limit cycle oscillation and how to perform zero input limit cycle oscillation. If you understood this video, kindly share with your friends. Thank you.